There is a place on this planet called the Mariana Trench. Most people have heard of it. Almost no one understands what it actually is. It is not simply a deep part of the ocean. It is the deepest place on the surface of this entire planet. A wound in the Pacific sea floor so extreme, so far beyond any other environment on Earth, that the life we expected to find there was essentially nothing. The models were clear. The physics was unambiguous. The science agreed. Then a camera went down, and the science stopped agreeing. The Mariana Trench sits in the western Pacific Ocean, east of the Mariana Islands, approximately 1,600 kilometers east of the Philippines. At its deepest point, a location called Challenger Deep, the ocean floor lies 10,935 meters below the surface. 10,935 meters. If you took Mount Everest, the tallest mountain on Earth, 8,849 meters from base to summit, and placed it at the bottom of Challenger Deep, the peak would not reach the surface, not even close. There would still be more than 2,000 meters of ocean pressing down above it. A camera went to the bottom of that place and found something that should not have been physically possible. The Mariana Trench is not a random feature. It is the result of one of the most powerful geological processes on Earth. The Pacific Plate, the largest tectonic plate on the planet, is moving westward at roughly 7 centimeters per year. At the Mariana Islands, it collides with the Mariana Plate. The older, denser Pacific Plate does not stop. It bends and slides underneath. This process is called subduction, and over tens of millions of years, that continuous downward bending created the trench we see today. It is 2,550 kilometers long, at its widest, 69 kilometers across, and at its deepest point, Challenger Deep, it is nearly 11 kilometers straight down. To understand what 11 kilometers means, you have to understand what the ocean becomes as you descend through it. The top 200 meters, the sunlit zone, is where almost all ocean life exists. Every whale, every shark, every coral reef, every creature you have ever seen in any nature documentary lives in the top 200 meters. Below 200 meters, sunlight begins to fail. By 1,000 meters, it is gone. Not dimming, gone. Absolutely and permanently. Below 2,000 meters, the midnight zone. Bioluminescent organisms create their own cold light. But it is biological light, not solar. The sun, up here, is irrelevant. Below 4,000 meters, the abyssal zone. Temperature, between 1 and 4 degrees Celsius, permanently. Pressure at this depth is already enough to crush a non-reinforced steel hull. Below 6,000 meters, the Hadal zone, named for Hades, the underworld. Named with precision, not poetry. The Mariana Trench descends nearly 5,000 meters below where the Hadal zone begins. At Challenger Deep, the water pressure is approximately 1,086 times the atmospheric pressure you are experiencing right now. That number is difficult to hold. So consider this instead. A standard styrofoam cup, 12 centimeters tall, hollow, full of air, attached to the outside of a research lander and sent to 10,000 meters, comes back roughly the size of a thimble. The styrofoam is not crushed. It is not broken. The structure is still intact. You can see it under a lens. It is simply smaller because every molecule of trapped air inside it was forced out. Now imagine that happening to your lungs. Your ribcage would not crack. It would simply cease to exist. The first humans to reach the bottom of the Mariana Trench did so on January 23, 1960. Their names were Don Walsh, a lieutenant in the United States Navy, and Jacques Picard, a Swiss ocean engineer. Their vessel was called the Trieste. The Trieste was a bathyscaphe, a steel observation sphere, roughly the diameter of a small wardrobe, welded to a float tank filled with aviation gasoline for buoyancy. The gasoline was not fuel, it was ballast. Gasoline is lighter than water. It keeps the vehicle afloat. There was no propulsion system, no steering, no communication satellite. Their connection to the surface ship was a telephone cable. The descent took 4 hours and 48 minutes. At depth, the forward observation viewport developed a crack, not a failure, not an emergency breach, a hairline fracture. In the only window between them and 1,086 atmospheres of pressure, Walsh and Piccard reviewed the crack, determined it was in the outer pane of a double-layered port, and decided to stay. They spent 20 minutes on the floor of the world. Then they rose. Don Walsh was 28 years old. Researchers who have made deep descents in the decades since have developed a small tradition. They attach styrofoam cups to the outside of their vehicles to show passengers, students, donors, first-timers, what pressure does. Those cups, returned from depth, make extraordinary paperweights. Some of the cups from very early expeditions were left at depth, intentionally, as markers. They are still there, on the floor of the Mariana Trench, in perfect condition. The cold, the pressure, the absence of any organism equipped to break them down, perfectly preserved, thimble-sized, waiting. For most of the 20th century, the scientific consensus on life in the Mariana Trench was orderly. Below approximately 8,000 meters, what researchers call the ultra-deep Hadal zone, the combination of extreme pressure, near freezing temperatures, and profound nutritional scarcity was expected to create a biological ceiling, a depth beyond which complex life simply could not function. Microbes, yes. Simple organisms, possibly. Anything with organized tissue. A nervous system, a skeleton, organs, no. The models were compelling. The mathematics was clean. And then someone sent a camera. Sending a camera to the floor of the Mariana Trench is not a photography problem. It is an engineering problem of the first order. You cannot use a standard remotely operated vehicle. The tether cable required to reach 11,000 meters would weigh more than the vehicle could carry. You cannot use a submarine. Military submarines are typically rated to depths below 600 meters. The Challenger Deep is 10,935. What researchers use instead is called a free-fall lander. A free-fall lander has no propulsion. It falls straight down, under gravity, weighted by ballast plates. The descent to Challenger Deep takes between 4 and 6 hours. The camera housing used in Hadal research is typically titanium, one of the few metals that combines high strength with resistance to pressure-induced compression. The viewport glass must be rated beyond the expected depth, because at these pressures, safety margins must be absolute. There is no communication during descent. No signal penetrates 11 kilometers of water effectively. The lander goes down alone, in the dark, in silence, for hours. Getting the lander to the bottom is solved by gravity. Getting it back is where the engineering becomes genuinely extraordinary. To return to the surface, the ballast weights must be released. Without them, the lander is buoyant. It rises. This release is triggered acoustically. A signal transmitted from the surface ship, propagating through 11 kilometers of water column to a receiver on the lander. If the signal fails to penetrate the water column correctly, the lander does not surface. If the acoustic release mechanism is damaged by the pressure, the lander does not surface. If the lander is carried by deep-sea current during its bottom time, it may surface kilometers from the recovery vessel, beyond radar range, gone. Researchers have a recovery window from the surface, generally 6 to 8 hours before drift and current make retrieval impossible. After that window, the lander and its footage belong to the Mariana Trench permanently. In 2023, a research team led by Dr. Alan Jamieson of the Minderoo UWA Deep Sea Research Centre at the University of Western Australia deployed a free-fall lander system into the Izu Ogasawara Trench, a Hadal trench in the Northwest Pacific, structurally connected to the broader Mariana Arc system. The goal was Hadal Biological Survey, document what lives at extreme depth, map the species distribution, extend the biological record. The lander descended, the cameras recorded, the acoustic release was triggered, and then the recovery team waited. The surface vessel held position. The sonar tracked for a return signal. It surfaced, and on the footage, at a depth of 8,336 meters below the surface, was a fish. Its name is Pseudoliparis beliaevi, common name, a snailfish. At 8,336 meters, it is the deepest fish ever recorded by camera in the history of ocean science. It is pale, almost translucent, built roughly like a comma, a smooth, tapered body, no scales, no rigid external structure of any kind. It has no swim bladder. The swim bladder is the organ most bony fish use to regulate their position in the water column. At 8,000 meters of pressure, a swim bladder would compress and collapse. Evolution solved that problem before we knew it existed by removing the organ entirely. It is pale because color costs energy. In an environment where nothing can afford waste, the body wastes nothing. No predator to hide from. No mate to attract with pigmentation. No light to reflect anyway. Color in the Mariana Trench is a luxury the body stopped paying for roughly 400 million years ago. The snailfish's survival is not accidental. It is biochemically engineered. Research by Dr. Paul Yancey and colleagues, published in the Proceedings of the National Academy of Sciences, identified the key mechanism. It is a compound called TMAO, trimethylamine oxide. TMAO is a pressure-stabilizing molecule. Under extreme pressure, proteins, the molecular machinery of life, begin to distort. Their three-dimensional shape, which determines their function, collapses under the force. TMAO counteracts this. It holds proteins in their functional shape despite the pressure bearing down on them. Every cell in the snailfish contains TMAO, and here is the detail that changes the story. The deeper you go, the higher the TMAO concentration in Hadal organisms. The body titrates the compound to the depth. More pressure, more TMAO, perfect function maintained. It is one of the most elegant adaptations in the recorded history of biology. If a vertebrate fish lives at 8,336 meters, the next question is immediate. What does it eat? The answer begins 11 kilometers above it. Every organism that dies in the sunlit zone, every phytoplankton, every copepod, every whale, eventually sinks. Scientists call this process marine snow, a slow perpetual precipitation of organic matter descending from the productive surface through every zone of the ocean, settling eventually on the floor of the Hadal Trench. By the time it arrives, it is not much, but it is enough to sustain populations of amphipods, tiny crustaceans related to shrimps and crabs, which congregate on the Hadal floor in densities that consistently surprise researchers when the bait cameras come back with footage. The species Hirondelia gigas has been documented at Challenger Deep in swarms numbering in the hundreds per square meter. The snailfish eats the amphipods. The amphipods eat the marine snow. The marine snow comes from the sun, a food chain that begins in sunlight and ends in the darkest place on Earth, connected, unbroken, functioning. The snailfish at 8,336 meters was extraordinary. It rewrote records. It generated headlines across every major scientific publication. But among researchers who study extreme environments, the snailfish, as remarkable as it is, fit inside a theoretical framework. It was a vertebrate. It had TMAO. The mechanism was understood if the record was broken. The thing that generated genuine scientific debate was not the snailfish. It was what the cameras found in the Mariana Trench itself. Something soft-bodied, something gelatinous, something that, by the established science of pressure biology, should not have been there. This is not the first time the deep ocean overturned what biology considered settled. In 1977, a submersible called Alvin was exploring the Galapagos Rift on the floor of the Pacific Ocean at approximately 2,500 meters depth. What researchers expected to find: cold, dark, nearly lifeless sea floor. What they found instead: hydrothermal vents, superheated water, mineral-rich, venting from the ocean floor at temperatures up to 400 degrees Celsius. Surrounding those vents, entire ecosystems, tube worms, giant clams, shrimp, crabs. A complete functioning biological community powered not by sunlight, but by the chemical energy of the Earth itself. Chemosynthesis, life without the sun. It was, at the time, described by the lead researcher Jack Corliss as the most significant marine biology finding of the century. It rewrote the definition of a habitable environment. What the cameras in the Mariana Trench are now recording suggests it may need to be rewritten again. Here is why this matters beyond ocean science. Jupiter's moon, Europa, has a subsurface ocean, kept liquid by tidal heating from Jupiter's gravitational pull, covered by a shell of ice estimated at 10 to 30 kilometers thick. The ocean beneath that ice is estimated to be between 60 and 150 kilometers deep. No sunlight reaches it, no warmth from any star. The pressure at its floor would exceed anything in the Mariana Trench. Saturn's moon Enceladus has a subsurface ocean too. Its geysers, observed directly by the Cassini spacecraft, vent water vapor and organic molecules into space. Organic molecules, the chemical vocabulary of life. For most of the 20th century, the argument against life on these worlds was simple. No light, no warmth, no life. The Mariana Trench ended that argument in 1977. The cameras descending into it now are narrowing the conditions under which life cannot survive. And the narrower that set of conditions becomes, the larger the universe of places where life might exist. The people who do this work are not famous. Dr. Alan Jamieson has spent more than 2 decades studying Hadal environments. He has published research that has fundamentally changed what biology knows about pressure adaptation, deep sea food webs, and species distribution in Hadal trenches. He has done most of this work with equipment budgets that would not sustain a single week of a major pharmaceutical research trial. The lander technology used in recent Hadal expeditions costs a fraction of a percent of the budget of a Mars surface rover. A fraction of a percent. We have spent more money looking for life on other planets than we have spent looking in the deepest parts of our own ocean. The ocean, as of 2023, is answering back. Below the snailfish, below the amphipods, below the cnidarians. In the sediment itself, the thick, fine-grained mud on the floor of Challenger Deep lives an entire separate community that researchers are only beginning to characterize. Bacteria, archaea, microbial communities producing compounds that have no equivalent in any shallow water species studied. Some of these compounds are being investigated for pharmaceutical properties, specifically antibacterial activity against antibiotic-resistant pathogens. The organisms that have evolved to survive at the bottom of the Mariana Trench may carry biochemical tools that medicine has been searching for in far more accessible environments without success. The Mariana Trench is not simply a deep hole. It is a pharmaceutical library that has never been properly catalogued. The Mariana Trench is 2,550 kilometers long. In the entire history of deep ocean research, the total area of the Hadal zone that has been directly surveyed by camera and sampling equipment represents less than 1% of its full extent. Less than 1%. We have sampled a postage stamp on a document the size of a continent and declared that we understand what is written there. We do not. What that 1% has revealed, the record-breaking fish, the soft-bodied cnidarians, the amphipod populations, the microbial communities, the pharmaceutical compounds, the geological dynamics, suggests that the remaining 99% contains things we have not yet developed the vocabulary to describe. We are not at the beginning of deep ocean science. We are at the end of the beginning. The Mariana Trench is not a passive feature. The process that created it, subduction, the Pacific Plate bending and descending beneath the Mariana Plate, is still ongoing, still active, still accumulating stress along the fault boundaries that surround it. The Pacific Ring of Fire, the arc of seismic and volcanic activity that encircles the Pacific Ocean, is, in significant part, a consequence of subduction. The same geological process that carved the Mariana Trench drives the earthquakes and tsunamis that affect hundreds of millions of people. The sediment accumulated in the trench influences the behavior of the fault. The water pulled down into the subducting plate changes how and where magma forms. The Mariana Trench is not separate from the world above it. It is one of the mechanisms that drives it. Before the freefall lander left the floor of the Mariana Trench, its camera recorded the seafloor. Not the snailfish, not the amphipods, the floor itself, the sediment, the particles suspended in the water column, the absolute, unbroken stillness of a place that has been this way for tens of millions of years. There is a quality to the stillness of the deep ocean that footage never fully captures. The water moves, but slowly. The particles drift, but without urgency. Nothing rushes, nothing needs to. At 10,935 meters below the surface, time moves differently, not physically, but the rate at which things change, the pace of biological activity, of chemical exchange, of geological development, is so slow as to be essentially still. The Mariana Trench has been dark for longer than our species has existed, and it has been alive for most of that time, without us, without light, without any of the things we consider necessary. The lander rises, 4 kilometers per hour, roughly, on ascent, through the Hadal zone, darkness, cold, silence, through the abyssal zone, more of the same, through the midnight zone, still dark, through the twilight zone, a faint, impossible blue begins. Not sunlight yet, the memory of sunlight. The first photons that have penetrated this deep. By 200 meters, the ocean is a different world entirely. Warm, productive, loud with biological activity, packed with the 99% of ocean life that never descends below the sunlit zone. The lander surfaces. The recovery team pulls it aboard, and on the memory card inside the titanium housing is footage from a place that most of humanity will never visit, never see, never know. Footage that required 400 million years of evolution to produce its subjects. In 1960, Don Walsh and Jacques Picard descended to the floor of the Mariana Trench and reported seeing a flatfish in the sediment. Later analysis suggested it may have been a sea cucumber. The visibility was limited. The time at depth, 20 minutes. They could not be certain. But the idea that something was alive down there stayed with the scientific community for 60 years. Now cameras go down regularly, not submarines, cameras. Small, patient, inexpensive relative to what they find. And what they find, every time, is more than the previous expedition recorded. More species, more behavior, more evidence that the definitions we have been using, the definitions that told us where life can and cannot survive, are not wrong exactly. They are just incomplete. The Mariana Trench covers an area larger than the continental United States. We have directly sampled less than 1% of it. No one knows what the other 99% contains. No one. A fish lives at 8,336 meters, using molecular tools that took 400 million years to build. Bacteria in the sediment of Challenger Deep produce compounds that may save human lives, and somewhere in the 99% of the Hadal zone that no camera has ever seen, something is alive. What do you think we will eventually find in the unexplored 99%? Subscribe if you want to keep exploring.